All right, this problem says let P be a prime, let FQ be a finite field of order Q, where Q is the prime power of the prime P, and for each element of our finite field, show that there exist uh, two other elements, A and B, such that X is equal to A squared plus B squared. So, in other words, we need to show that every element of a finite field is a sum of two squares. Okay, so let's break it into two cases. So if the characteristic of FQ is equal to 2, in other words, if our P is 2, um, then um, well, how can we argue? Well, since um, FQ is a field, the Frobenius map, which sends every element um, to every element x to the p, where p is the characteristic of our ring or field. Um, and the Frobenius map for a field is always injective. And since this is a finite field, it's also surjective. Frobenius map is not in general surjective, but for finite fields it is. Um, well, what is the Frobenius map in this case? The characteristic is 2, so it's sending x to x squared, right? So for that map to be surjective means that every element is a square. So every x in FQ is a square. Thus every and being a square yourself is good enough because we can just add 0 squared, which is another square that always exists. So thus every x in FQ can be written as a squared plus 0 squared for some a in FQ. Okay, so that case is easier. And now let's do the other case. So um, if the characteristic of FQ is not 2, then it's uh, some odd prime. And uh, in particular, the order of the field is going to be odd. And remember so what we're going to do is we're going to think about the uh, multiplicative group of our finite field. And remember that the multiplicative group of a finite field is cyclic, and consists of all those elements except for 0, because only 0 is not invertible in a field. So note that FQ cross, the multiplicative group, is cyclic. And importantly, since FQ it is odd, then the multiplicative group where we take away 0 is not only cyclic but also of even order. And if you're a cyclic group of even order, then what must be true? Well, exactly half of your elements have to be squares. Exactly half of its elements are squares. Um, Now, note that the zero element of our field, is also a square. So how many squares do we have at least? So the set of all a squared such that a is in FQ, set of all squares, well, the cardinality of this has to be at least q plus 1 divided by 2, or in other words, more than half of the size of our original field of our field FQ. Um, and well, if that's true, then consider any fixed x. For any fixed element x, for any fixed x in FQ, the cardinality of the set of all elements of the form x minus b squared such that b is in FQ. So I'm being a little bit loose in how I'm writing this, but I just mean all the elements of the form x minus b squared. Um, for some b and fq, well, there have to be at least as many as there are squares. Um, because if you had two distinct squares that gave you the same element when you did x minus them, well, that would just contradict um, the that x is some fixed element. Um, so uh, this set also has to um, have cardinality at least q plus 1 over 2. Okay, well, we only have q many uh, elements in our field, and so if this set has size more than half and this set has size more than half, then these sets must intersect, right? Um, so the above sets have non-empty intersection, i.e., for any fixed x, there exists a and b such that a squared is equal to x minus b squared, or in other words, x is equal to a squared plus b squared. And that gives us what we were looking for.